Okay, so in the last section we came up with this equation for the displacement of a simple harmonic oscillator. So let's just have another look at an oscillator, a simple harmonic oscillator. Well, remember that to come up with this equation, we released the oscillator when x was at the maximum displacement, or the amplitude A. And that's important. This equation is only true when that's the case. So it's only true if x equals plus A, maximum positive amplitude, when t equals 0. Otherwise it doesn't work, and we'll see how to deal with that later on, like if the clock starts at a different time. But for the moment, this is what we're doing. Well, okay, so we get this kind of thing, that the displacement is given by A cosine theta, and theta, of course, is omega t, and omega represents the angular velocity of something going in a circle with the same time period as our oscillator. So it is pretty abstract. So let's dig down and kind of see how this kind of tells us our actual displacement of our oscillator, because our displacement is just like a value between minus A and plus A. And that's what we're desperately trying to find out at any given time. Okay, so, well, the graph of that motion, we can guess is going to kind of look like a cosine graph. Here's some axes, but let's see why. So for the moment, we've just kind of drawn a graph for the displacement against time. And we're going to just see if we can calculate using our expression where the displacement should be at any given time. Remember, of course, that there are other ways to write this, because we know, for example, that omega is 2 pi over t. So I could write A cosine 2 pi over t, t is the time period, times t, instead. Or, for that matter, I know that omega is 2 pi f. So another common way to see this written is A cosine 2 pi ft. So there's a whole bunch of ways. Remember, of course, that brackets are kind of implicit here, and they're not normally drawn. But everything to the right of the cosine is like being cosines, if you know what I'm saying. Okay, well, the one that we're going to find particularly useful today is this one, where we rewrite omega as 2 pi over t, and it just makes the whole thing a bit easier to understand, because remember that t relates to the oscillator. We understand what it means, the time period of the oscillator. It's the time to go all the way through its cycle. Great, okay, so let's get a table going, and let's see if we can calculate the displacements at various different times. So here's my time. Of course, that would be measured in seconds. And what we want to come up is our displacement, which of course would be in meters. And so we've decided that we're going to use this equation, A cosine 2 pi over period times t, to get our displacement. So the first step is to find out what that angle is for different time periods. So I'm going to choose a few time periods here. We're going to find that time equals 0. We're going to find out what the displacement will be at a quarter of a cycle, a half a cycle, at 3/4 the way through the cycle, and at a full cycle. Because we know those, we can kind of guess them already. For example, at time equals 0, we're releasing it from plus A, so we actually know that answer already. And we know it's going to end up back there. But let's see how the equation works to give us that. That's what's really important. So first up, let's see what the time gives us for our angle by writing down our angle here, theta, in our new kind of form that we've chosen, 2 pi over t. So theta, which is really 2 pi over the time period, because that's omega, times t. And that's going to be really interesting. So let's go for it. Let's plug in our values. Well, if time is 0, then we're going to get 2 pi over the time period times 0. And that is obviously 0. No surprise there. And when time is t by 4, then we're going to get t pi over t times t by 4. So a quarter of a way through the cycle. And you can see that that's kind of going to come out as pi by 2. Interesting, because that looks like a familiar angle to us. of course, in degrees, this is in radians, remember, because omega is in radians per second. In degrees, well, let's just put a column for degrees, because it's worth just knowing that. Let's put theta in degrees. Well, let's put it in brackets, because we're really working radians, but it doesn't matter. Well, 0 in degrees is 0. Pi by 2 is 90 degrees. Okay, let's do the other three. You might want to pause, see if you can calculate the angles for half a period, 3/4 of a period, and a whole time period. Okay, so did you have a go? Let's see what our values are. So at half a time period, we've got 2 pi over t times t over 2. And that just gives us pi. And at 3/4 a time period, we get 2 pi over t times 3t over 4, which gives us 3 pi by 2. And finally, at a whole time period, we get 2 pi over t times t, which is 2 pi. So all of those kind of radian angles kind of look familiar from when we looked at radians. Let's write down their equivalents in degrees. Again, see if you can pause and write them down. See if you can remember how to do those conversions. So pi is 180 degrees, 3 pi by 2 is 270 degrees, and 2 pi is 360 degrees. Well, the next thing we need to do is just to write down what will be the cosine of that angle. So what would be our cosine theta? Or, as we're expressing theta at the moment, our cosine of 2 pi over t times t. Well, straightforward, because we can use our calculators and we can put in our radian angles, but you'd have to convert your calculator into radians. So you could do cosine of 0 in radians or degrees will give you 1. Cosine of pi by 2 radians, well, if you're calculating radians, then you'll find that you'll get 0. And of course, we could do it in degrees. Cosine 90, when you're calculating in degrees, would also give you 0. So see if you can get the other values. And yes, you should have found -1, 0, and +1. And of course, finally then, we can complete the right-hand side column, because the displacement then is the angle, the cosine of the angle, times a. So, well, 1 times the a is just going to give us +a, same at the bottom, and we can fill in all the other values now. So we're going to get 0, -a, 0, and +a. And at last, we've got enough information to kind of prove that our graph is indeed the cosine that we expected to see. And why that's so? Well, at time equals 0, we've got +a, then it goes to 0 at t by 4, -a at t by 2, 0 at 3t by 4, and +a again at the time period. And we can draw our nice cosine, we could work out all the values if we wanted, but that's good enough. We can put in our nice cosine, which is just going to repeat. And so that's it. So we've seen, hopefully that makes it clearer how this equation works. What we're going to do next is look, well, what if we start the clock at different times when the body is not at its maximum positive displacement, but at another displacement?